Hello and welcome to lecture number 11. So in this lecture we are going to find the important implications of the Kelvin equation. So I remember in the last class we tried to derive the Kelvin equation, which is this one. So it is applied on a curved surface. So remember we were discussing the phenomena at the curved surfaces. So RT multiplied by natural log of P over P naught. So by definition, P naught is the vapor pressure is equal to the pressure of the liquid on a plane surface. And when the plane surface gets curved, so we can assume that we have a convex surface, for example. So the vapor pressure also changes to P and the pressure of the liquid changes to P1. So this equal to the molar volume of the liquid multiplied by the pressure difference between the curved liquid minus the plain liquid. Okay, so the pressure difference is the pressure of the two liquids, one at the curved interface and one at the plane interface. So today we are going to see that how this delta P liquid, this one, is related to the radius of the curvature of the curved surface, assuming that we are talking a spherical surface. Alright, so our point is, let's assume that this surface is spherical one and perhaps this is the radius of curvature. So what is the relationship between this radius and this delta P liquid? So for that we are going to have a short derivation of another very important equation, and the equation is called the Young-Laplace equation. But today we are not going to derive the Young-Laplace equation exactly in the way it was done by Young and Laplace, but we are going to deal it by a much simpler fashion. Okay, so we do that by taking an example of a soap bubble. Okay, so imagine we have a soap bubble, so where the surface consists of a soap film. All right, so if you remember when you were younger, so probably we used to make soap bubble by dipping a straw or pipe or a loop made by wire into a soap solution, and if we pull it out we would find a thin film at the cross section of that loop or the straw. Then we used to blow air to inflate that bubble. So now whenever we are pushing air into the bubble, so that means the pressure inside of the bubble must be higher than the pressure outside. Okay, when the bubble is actually gaining its volume, that means it is being inflated. So therefore when the bubble is expanding, so during the expansion, obviously the pressure inside should be greater than the pressure outside. And if you blow it too much, the bubble would burst. But at certain point, a complete bubble is formed and it gets detached off from that loop, and it floats in the air. So that means when we are talking about a stable bubble. So for a stable soap bubble, the net pressure inside this surface, okay, so the pressure exerted in the surface, it is P, so we can write like this way: the net pressure for a stable bubble, the net pressure exerted on the inner surface is equal to P inside minus P outside. Alright, so this pressure has to be balanced by something else. Otherwise, you don't have a stable bubble. So the question is, what other force is equalizing this net pressure? Because this bubble cannot continue to grow forever. So can you imagine what is that stabilizing force? So the stabilizing force that actually opposes the growth of the air bubble forever is actually the surface tension of the soap. So to derive a relationship, we can think about that we have a soap bubble and we divide the soap bubble into two hemispheres if we take the cross section of it. So now we can think that the pressure, which is the force which is exerted towards the inner surface, like these forces, okay. These forces would try to separate the two hemispheres from each other. All right. So now let's think about a particular lobe, that means the upper hemisphere. So we can write the rupturing force of the bubble that is working on the upper hemisphere is equal to, so force means pressure multiplied by area. So this is the net pressure, that is P inside minus P outside, and we are talking about a stable bubble, multiplied by the force that is acting through the cross section of this hemisphere. So the cross section is pi r square. All right. So now the thing is, this force has to be equalized by a stabilizing force. So the stabilizing force that is actually trying to hold the two hemispheres together is actually the surface tension gamma, and the surface tension gamma is would actually be acting again in the opposite direction of this rupturing force, and it would be acting all along the circumference of that cross section, means the circumference of the circular cross section. So therefore we can write the stabilizing force should be gamma multiplied by twice of pi r. So of course I had to tell that the radius of the spherical bubble is considered to be r. Is that all? We have to multiply again this thing with a factor 2, because see there are two surfaces now, one at the outside and another at the inside. So because this is a thin film, so the thin film of soap interfacing air on both ways, both sides, so the outside of the bubble and also the inside of the bubble. So therefore, as I told you before, that if there are two types of surfaces, we have to think or consider about the surface tension twice. So therefore this factor is being multiplied by 2. So at equilibrium, what would happen? The rupturing force, that is P in minus P out, which we call the delta P pi r square, is equal to 4 gamma pi r. Or in other words, if we think about delta P, okay, so this pi cancels out, and r, here we have r, so delta P is equal to 4 gamma divided by r. Now this is for a soap bubble which has two surfaces. But if we expand this delta P for liquid, or in other words, if we have a water droplet or liquid bubble, so a water droplet, so we can call it a liquid droplet with the radius of curvature r. We can think about the spherical liquid droplet with the radius r. Then remember, it has only one surface. It is the liquid air surface. So therefore, in the same derivation, we don't have to multiply it with by the factor 2. So therefore, here the delta P liquid should be twice of gamma divided by R. Alright. So therefore, we come at a conclusion that the pressure difference of this curved surface of the liquid versus the plane surface, so that is given as the delta P. That means the outer surface, that is the P outer, can be taken equal as the pressure on a plane surface. That means pressure at the on a liquid that is having a plane surface. So the same thing, the delta P can be expressed as like I wrote earlier, P1 minus P0. So we have an expression 2 gamma by R, and so this equation is actually also comes from if we have a direct derivation of Young-Laplace equation. So we also come at the same expression. So we can also call it that this expression is actually a part of Young-Laplace equation for liquid, assuming to be spherical with a radius of curvature r. Alright. So now the original Young-Laplace equation can be actually denoted by something like that. So it is like delta P is equal to gamma divided by 1 over R1 minus 1 over R2. So sorry, 1 over R1 plus 1 over R2. So where this R1 and R2 are the two different types of principal radii of a curved surface. So we are only assuming spherical. So here R1 is equal to R2, but there are other types of geometrical shapes where we can have two different two principal radii. So R1 and R2 are referring respectively the two different curved surfaces. Anyway, so now with this information, that is delta P liquid is equal to 2 gamma by R, we have now convert, or we can now merge the Kelvin equation with Young-Laplace equation. And after cleaning the board, I'm going to write now the newly found modified Kelvin equation in terms of surface tension and R, and we would like to see what implications this equation bring to the context. Alright, so let's do that here. So when we combine the Kelvin equation with Young-Laplace equation, we get the final form like this. So this equation is valid for a spherical surface with the radius of curvature r. And now from this equation we can easily understand that when P tends to P naught, that means whenever P is equal to P naught, so this term becomes 0. So this term 0 means, if you look at here on the right hand side, so this is constant, so that automatically implies that R should be infinity. So R infinity means the radius of curvature is at infinity. So this automatically implies that we have a plane surface. Right? Now, whenever R is not infinity, whenever R is finite, obviously we have, for any positive value of R, we have P greater than P naught. Okay? For R is equal to positive. So, or we can write, So this is for a convex surface, and P would be less than P naught, obviously, for R is equal to negative, or we have a concave surface. Alright. So now the question is, what is the implication of the Kelvin equation in a practical life? So if you look at this here, the left hand side, I have written some data. So here on the left column, I have noted radius in terms of meter, and in the right hand column, I have P by P naught value. So it's a fraction greater than 1 because I have listed all positive R values over here. So here this is 10 to the power minus 6 meter, that means micron. Okay, so this is the micron value, and this is a nanometer value, 10 to the power minus 9. So you see, when radius decreases, the radius of curvature decreases, that means this value is smaller, so the overall term becomes more positive or becomes higher in magnitude, and it also gives that P by P0 would be greater. So therefore, you see that accordingly the P by P naught value increases from 1.001 to 1.01 to 1.11, and whenever the radius of curvature becomes very small, it's nanometer, you see this has a very high value, 2.7. P by P naught is equal to 2.7. Now what happens? So there are no practical implications. So now you think that this P in other words, the P naught is the vapor pressure in the atmosphere. All right. So in the early morning or in the winter season, at the specified temperature, this the existing vapor pressure in the atmosphere gets saturated. All right. So, and if we think that the pressure P is the pressure of the curved surface, okay. So, what happens then slowly? Whenever we have this P by P naught value, it can initially it may be P by P naught may be below 1 initially, and slowly, so below 1 means it could be around say 0.99 or something, that means it is approaching 1. And then once the atmosphere is more saturated with vapor pressure, so this P by P naught value gets increased, so it can even go beyond 1. So at that point what we see that in the early morning of winter or in autumn, we see the dew formation. Okay, so that means the formation condensation of vapor into liquid droplets. So interestingly, whenever the P by P naught value is around say 0.99, that's below 1. So my mathematics says that whenever P is less than P naught, the R is negative. That means we should have a concave surface if the liquid condenses. So exactly what happens that whenever dew forms at P by P naught less than 1, okay, so remember here, that means the dew formation just started, but the atmosphere is not fully saturated with the vapor pressure. So the condensation occurs with a concave surface. So the cracks and crevices of the soil or rocks, okay, or woods, you will see whenever there is a crack like that, the water will condense with a negative meniscus, and this negative meniscus is a result of the Kelvin equation. And then whenever P by P naught just touches 1, so it is something like 1.00001, that means it has touched 1 and it's just a touch above than 1, then dramatically this negative meniscus changes to positive meniscus. So therefore, whenever say you can think that if P by P naught value is something 1.0001, something of value like that, that means it's just above 1. So theoretically, at this point, the R value should be, if you go by this trend, so we can say that the R value is something around 10 to the power minus 3 meter. Okay, so that means this is actually millimeter, and millimeter means bulk size, we can see. So when the atmosphere, so this we can see that this is the Earth surface, and water has condensed as a dew. So we have a water droplet, but the water droplet will have a convex surface. Okay, so we have a positive meniscus here, and this is obviously convex surface, and this convex surface is occurring due to this formula, that is P is greater than P naught, and we have the R positive value. So now if we look at this picture once again, so I am just erasing this part over here. So once again I am drawing the formation of the dew. So either the dew can take place of shape like that, or the dew can take the shape something like that. Now whatever, whether the shape would be like this or like that, it would depend on whether the surface is hydrophobic or hydrophilic. But no matter what, the one thing is in common, that it would have a convex liquid surface, and this happens due to a science or mathematical expression which is known as the Kelvin equation. And this kind of liquid droplet scientifically is called a sessile droplet. So now you know that why the sessile droplet will always have a convex surface at P by P0 greater than 1, and whenever P by P0 is less than 1, the same dew droplet will form into the cracks and crevices on Earth's surface like that, with a negative meniscus. Alright, so it is perfectly in accordance with the mathematics, that is the Kelvin equation. So now we are not done yet with the implications of Kelvin equation. So there is an interesting scenario if we look at these data over here. Okay, so I am going to erase this part of the board and let's continue discussing on this. So if you look at the data on the left hand side, that whenever for a liquid droplet of a nanometer dimension, okay, so you imagine this R is actually in the order of nanometer. Then this is the atmosphere. Okay, so let's write like that. So P by P is naught. So P naught is the pressure of the plane surface, and P is just the pressure inside, or pressure at the convex surface or curved surface. So it says that this P by P0 should be around 2.7. Okay, so remember, if we talk about atmospheric science, or if you think that P0 is 1 atmospheric pressure. So if we talking about a liquid droplet formed in air, then P0 should be around 1 atmosphere. Then according to Kelvin equation, it demands that P should be 2.7 atmospheric pressure. So can you imagine that? 2.7 times of the atmospheric pressure. So why I'm talking this? I'm talking this because have you ever think about cloud in the atmosphere? So cloud is nothing but a collection of condensed liquid or water droplet. Alright. Now experimentally it has been seen that the size of these water droplets in cloud varies between nanometer to micrometer region. So that means, so this is the micrometer region and this is the nanometer. It's more towards the nanometer size. Okay, so we'll continue this discussion just for a short break. Okay, so let's resume our discussion. Cloud droplets are mostly nanometer size range. So, but how on the atmosphere is it possible to have almost 3 times of the normal atmospheric pressure for the water molecule to be condensed as cloud droplets for a size around the radius of a few nanometers? How is it possible? So therefore, we need to bypass that energy barrier. So that means, so the question is how to overcome the pressure barrier to form clouds, because it is very important to understand what is the science behind the formation of cloud, because it needs very high pressure, and at the free atmosphere we cannot have such high pressure. Then how do the clouds form? So the clouds form, they actually have to bypass this pressure barrier, and the mode of bypass is once again the presence of a surface. So that means mainly solid surface. So you need a solid surface just to act like a catalyst. That means it will offer an alternate pathway with low energy barrier. So we can think about this high pressure as a very high activation energy. We can think of that is it is just an analogy. So analogous to that, whenever we have a solid surface present, we don't need to have this 2.7 times high atmospheric pressure. So around that solid surface, the liquid droplets can easily condense. So that solid surface acts as a support. Right. So who provides that solid surface high in that atmosphere? The answer is simply the dust particles or the aerosols. So you see one thing, dust particles suspended in air high in atmosphere are always not that bad. Okay, you need some to form the cloud, and that is also an implication of the Kelvin equation. And obviously without clouds we won't have rain and we cannot survive. So we have learned a few important implications of Kelvin equation in practical life, and there is one more applications of the Kelvin equation in a slightly different context involving solubility, not directly with pressure, and so that is a different phenomena. And now I'm going to release the board and I'm going to talk that phenomena, because it is just an extended application of the Kelvin equation. Alright, so let's write that equation and quickly discuss. So now we are about to learn another very important implications of Kelvin equation, which is the enhanced solubility of solid particles. So here we are extending the concept of Kelvin equation from liquid to solid. So therefore, since solid behave quite differently than liquid, So the equation changed a little bit, but the basic structure is the same. So RT, natural log of x over x naught. So instead of p over p naught, we have x over x naught. And so let me explain what are x and x naught later. Multiplied by V. Vs is the molar volume of the crystalline solid. Multiplied by, instead of 2 gamma by R, we have 6 gamma by A. So what is A? A is the A are the particles with crystalline dimension. So this A is in range of angstrom. And remember, A can be, for a cubic particle, A is the length of the sides. For a spherical particle, A is the radius. So it's the dimension. And gamma is the surface tension of the solid. And or we can say the interfacial tension of the solid, because if it interfaces with water. So this is the equation, and then X is the molar solubility of the particles when A is equal to infinity. That means if we have a flat plane surface, then whatever the molar solubility, so this is denoted as I think there is a little bit change in here, so it should be x naught here. So yeah, it should be x naught. So when the molar solubility is at the so we have a plane surface. Okay, that means we're talking about bulk materials. And so x is the molar solubility of particles with crystalline dimension A. So if we look at the equation here, so if we make the A to be smaller the A is, then this fraction would be very high, the large value. Okay. So whenever it has this term is a very large value, so this means here that x must be high. So X is what? X is the molar solubility of particles with crystalline dimension. So the crystalline particle, it can be a nanocrystal. So that crystalline particle will have enhanced solubility in the water. And so therefore it will try to get dissolved. So the implication of this equation simply, if we have a smaller and smaller crystalline particle, if it has been made from an aqueous solution by precipitation method, that means by saturating the solution, this crystalline particle would dissolve and go back to the solution, and it can make the solution supersaturated. So here is an example, so an illustration I am talking about. So let's think that we have a saturated aqueous solution of, say, ingredient like silver nitrate and potassium chloride, something like that, or barium chloride or sodium sulfate, something like that. If we mix the two, obviously by simple chemistry we expect some freshly precipitated fine powder of silver chloride solid or barium sulfate solid. But when they precipitate, they form actually very small particles. So some are very small nanoparticles and some are microparticles like this. So its radius could be nanometer and its radius could be micron. Because these are freshly prepared particles, finely suspended. So now what happens, according to this equation, particles with smaller A will have high solubility. So that means this X is high. So high solubility means the particle would get dissolved into the saturated aqueous solution. So that means these particles would start to smaller particles, or rather I would say the smallest particle would be the fastest to get vanished from the solution by getting dissolved back. So now whatever it was the saturated aqueous solution, the saturated aqueous solution would now turn into a supersaturated solution. So at the supersaturation, obviously what would happen, that the existing particles, whatever the bigger particles, okay, so this bigger solubility So the with respect to these bigger particles, yes, the solution would act or behave as a supersaturated one. So now what happens? Once again, because this solution is already supersaturated, so it cannot hold any more ions. So those ions again from the solution would start to get deposited, and for deposition it needs some solid surface. So they choose the existing bigger particles and they starts to get saturated on its surface like that. All right, and then what happens? These particles starts to get bigger, and once again it starts to get bigger. Again, the solution gets back from supersaturated state to saturated state, and in that condition, once again, whatever there are some next available smaller particle, it would happen that its x would still become high. So again those smaller particles would get dissolved and the same cycle would continue. So such solution would get supersaturated, and again there will be some deposition in bigger particles. So the solution comes back to saturated status again. So what happens? So after some time we would see that there would be no smaller particles, like no nanometer sized particles. The existing particle would try, with time, it would try to grow bigger and bigger and bigger. So what would happen, that a smaller particle, which means previously whatever it was, a smaller one, say like it was 100 or 200 micron, it would grow bigger into some micron size. So for here we can write that from few hundred nanometer, so it can grow into few nanometers. So a smaller particle can grow bigger like this. So the crystal grows bigger. So this entire process has a name. So it is also known as Ostwald's ripening procedure, or Ostwald's ripening process, where the larger crystal grows in size at the expense of a smaller crystal. And the entire science is actually explained by this equation. Now it so happens that the effect of Ostwald's ripening is most pronounced in a kind of a salt which is not very sparingly soluble. It has some kind of solubility. So calcium carbonate. So calcium carbonate solubility is way higher than silver chloride or barium sulfate. So therefore, it becomes so soluble that whenever we try to make a freshly precipitated calcium carbonate, the smaller particle would automatically vanish, and not only smaller, the X value is so high with respect to A that even like few micron size particles also starts to dissolve. So therefore, it is very difficult, it's almost impossible to have a finely suspended stable colloidal hydrosol for calcium carbonate because of extended Ostwald's ripening. Alright, so today in this lecture we have discussed quite a few interesting real life practical examples of the implications of Kelvin equation. So we had learned about the aspects of dew formation, cloud formation, and now in this case we have learned about the Ostwald's ripening. So Ostwald's ripening have deep impact in synthetic laboratory, especially nanosciences, because sometimes we want our nanocrystals to grow a little bigger, say from 10 nanometer to 20 nanometer to 50 nanometer, and sometimes researchers take the help of Ostwald's ripening effect. That means you simply have to wait or allow the crystal to grow in size from its ingredient solution. So researchers take the help of such ripening procedure to make a bigger nanocrystal from a smaller one, and all the science behind the ripening process is actually illustrated in the form of an equation, the source of which is nothing but the Kelvin equation. So in my opinion, understanding Kelvin equation is actually grabbing the core concepts of the colloidal science of solid liquid or liquid gas interface. So I hope you have understood it, and so we will stop it here today, and in next lecture, lecture 12, we will move on to uh, the another concept of liquid-liquid interface. All right, so stay put. See you in the next lecture. Till then, goodbye.